Okay. Okay, good. Say it again?
Co-host? Can you make us co-host?
Oh, okay. Like how, who? Let's make you co-host.
Yes, and we can maybe someone else also in case network connection is unstable.
Okay, sure. Sounds good. So how about Mohammed? Okay. Let me look at this also. Okay. I think we can get started. Oh, you guys are the brave ones who are here or didn't go home maybe due to the break and don't think the weather is attractive enough to skip this lecture. Okay, that's good. Now we know the design constraints, right? The reasoning. Okay, so we have only 3 lectures left. That's good or bad news, depending on how you view things. But today we're going to cover a lot of interesting things in caches. I call it advanced caches, but some of it is basic, some of it is advanced. Caching has a lot of literature, so there have been a lot of things that have been proposed. Clearly, we're not going to cover all of them, but I'll give you hopefully a lay of the land of what happens in caching and how to design them. Okay, let's see how much we can cover. I have some material at the end on multiprocessor caching, multi-core caching, which makes things even more exciting and much more difficult also, but we may not be able to cover that, and we may release a optional lecture if you're interested in that. Okay, so just a reminder, Amdahl's law paper is still up for, let's say, a review. And these are the readings that you're doing. I'll assign some more readings tomorrow when we talk about, not tomorrow, next week, when we talk about prefetching and virtual memory. And just to jog your memory, this is the memory hierarchy that we were talking about last time, right? And we discussed the reasons for the memory hierarchy. Basically, you have different levels in the memory hierarchy, and the goal is to get high speed, low latency, and high capacity at the same time. Ideally, if you manage this multi-level memory hierarchy well, you'll get the latency of the L1 cache while getting the capacity of main memory, essentially. That's the illusion that you want to provide to the programmer who assumes this is all transparent, right? That's what we said in cache management. But of course, this illusion is not easy to provide. So how do you manage this memory hierarchy? How do you manage each individual cache level matters. And sometimes you cannot even provide this illusion, right? And I think I will challenge you to think a bit critically and say, what if all of your accesses were completely random to random memory locations? You have no temporal locality, no spatial locality. This hierarchy is essentially useless in that case, right? And this is more and more what we're seeing in applications. Some applications have very heavy random access patterns. And as a result, this design that has been optimized for decades and decades is not working very well. That's why pushing computation towards memory also makes sense, especially in those applications where this hierarchy doesn't work well at all. Okay, so this is one view of the hierarchy. This is another view of the hierarchy. I'm going to expand it actually. Last time we discussed it. So you can see that register file is actually part of the hierarchy. You exploit locality. It's managed by the compiler manually. And you have multi-level caches. And then caches are also backed up to a swap disk, part of which can be in physical memory, part of which can be in disk, part of which can be even somewhere else. As I mentioned last time, but I didn't show you a picture, but maybe I'll show a picture right now. Memory hierarchy actually extends beyond a single server today, because especially if you look at large applications, data-intensive applications that are run on data servers, you really need so much memory capacity that you cannot fit that on a single server, single node. So what people do is they design special servers just for memory. These are called, for example, memory nodes, as you can see over here. And this enables even higher memory capacity. And now you actually have the local memory over here and the hierarchy, just like something like this. And then you have a remote memory that's another level in the hierarchy that you access through some low latency network. And today's networks are actually quite low latency. This could be microseconds, for example. It's not nanoseconds, but microseconds. So this is real actually in real systems today. Again, the reason is applications are extremely data intensive. So when I mentioned that computing today is bottlenecked by data, we were not joking. These applications are really so data intensive that you're designing memory hierarchies that look like this today in real systems. And this is an example of a memory blade designed as a memory. So you can see that this is a compute blade. It has what we have discussed so far, basically, a computation unit, CPUs, and memory hierarchy. They're showing the DRAM modules here. But then you connect that to memory blade so that you can expand the memory capacity. And then the memory blade may look like this. This is from this particular paper over here. So this is actually very interesting, and there's a lot of research going on in this area. We've been doing some research also. And if you're interested, this is the local memory over here. And now this is the remote memory, right? And that's part of your memory hierarchy across the data center, if you will. And if you're interested, there are papers related to it. And you can find a more recent work that we have done with VMware that actually has pointers to a lot of work in this area. Okay, but we're not going to talk about that. But it's good to think critically and see how memory is expanding in the system. Now let's get back to where we are. I'm going to jog your memory with the toy cache example we had. Remember that we designed a toy cache, very simple cache, not like terabytes or exabytes, just 256 bytes, if you remember. But doesn't matter. Even then, you have the similar trade-offs. And we said that in a direct map cache, a given memory block can be placed in only one possible location in the cache. And then we said that that's very inflexible because a memory block can map to only one possible location. And if there's a conflict in that location, some other block needs to be in the cache also because of your access pattern. You cannot house both blocks. So we made this set associative where a set can house more than one cache block, in this case, 2, as you can see. And then you can also have a fully associative cache where any memory block can go to any possible location in the cache, right? So basically, we introduced set associative caches. And set associativity is the idea that you have a set of locations where a memory block can map to. If that set of locations is 1, set associativity reduces to direct mapped. If that set of locations is all possible blocks in the cache, that set associativity means it's fully associative cache, basically. And we discussed the trade-offs of this last time. And we're going to pick up on those. And this is the 4-way cache. If you remember, this was the 2-way cache. Basically, a set consists of 2 possible locations. 4-way cache, a set consists of 4 possible locations. And a fully associative cache, there's no notion of indexing anymore. It's basically completely content addressable tag search. Whenever you place a block, you can place it anywhere. Whenever you want to find a block, you have to search every possible location, basically. As a result, this search is very wide, as you can see over here. We're just showing 8 blocks over here, right? In a modern cache, L3 cache, we will see later that people are building 120 megabyte L3 caches. If your L3 cache is 120 megabyte, if your block size is 128, you have almost 1 million blocks, right, in that cache. You can imagine doing that search for 1 million, having 1 million comparators. And the size of the comparator is not toy like this here. It's toy like 5 bits, right? But in real systems, the size of the comparator is at least 32 bits. So 1 million 32-bit comparators, you exercise every cycle, every time you access the cache. Doesn't sound very good. That's why fully associative is not easy to build, correct? Okay, and we discussed the trade-offs in associativity. Clearly, higher associativity can give you a higher hit rate, but it makes the design more complex and makes it slower. We also discussed that you get diminishing returns from higher associativity. This was a picture that I showed you on average across many workloads potentially, but if you look at each individual workload, the curve may be different, right? As you increase associativity, at some point your hit rate may jump from 0% to 100%. Why? Because you may be thrashing in all of your sets if you're, let's say, 4-way associative. But if you had 8-way associativity, you wouldn't be thrashing anymore. You would accommodate all of the conflict misses. Your hit rate in the steady state may jump to 100%, right? So different workloads behave very differently. Okay, and this slide, we discussed this actually, so I'll go through this relatively quickly. We're going to look at actually a lot of issues related to this. Basically, there are many issues in set associative cache, and we kind of built a framework on how to think about what to do with the blocks in a set associative cache. Each block can be considered to have a priority, and the key issue is really how do you determine and adjust the block priorities to decide which block do you insert into the cache or replace from the cache, right? And there are 3 decisions you have actually: insertion, promotion, and eviction. Eviction is called replacement. Insertion basically determines what happens to the priorities of different blocks in the set on a cache fill when you fill the cache. Where do you insert the coming block? Does it become the highest priority, meaning latest to be evicted, let's say, at that point in time? You even have a choice of whether to insert the cache block into the cache, right? You may actually just use the data and drop the cache block, right? And then there's promotion. Whenever you get a cache hit on a block, what happens to the priority of that block and other blocks? Do you change anything at all? We'll see in the LRU, least recently used replacement policy, you need to change that actually. Unless that block that you hit on was the least recently used, the most recently used, sorry. And then eviction replacement, this asks the question, what happens to priorities on a cache miss? Which block do you replace? And how do you adjust the priorities of the blocks inside the cache? Okay, and this was the last slide we looked at last time, right? And we were discussing basically which block do you replace on a cache miss. We're just looking at eviction replacement, but we may assume some things about the other two issues like insertion and promotion also. Like when I talk about least recently used in a little bit, I'm going to assume that you have an ordering across the blocks that tell you exactly which block is the least recently used, which block is the most recently used, and the order of the recency of use of the blocks. So that's clearly one way of deciding what to evict from the cache, least recently used one, right? That may make sense, right? Because when we motivated the cache, we said temporal locality. Temporal locality means that recently used items are supposed to be used again and again. That's the prediction or anticipation, which means that if you keep track of the least recently used blocks, you would expect them to be not used going into the future. As a result, why don't you evict those least recently used blocks? Of course, this works nicely if world was perfect, right? The access patterns are not always perfectly friendly to least recently used implementations. Okay, so I think we discussed a lot of these. I'll mention some of these again, but it's good to think about hybrid replacement policy. So the key is basically replacement policy or eviction policy or promotion policy or insertion policy. It's very much dependent on your access patterns, the benefits that you get. If your access pattern is completely random, for example, you don't have much benefit from caching. If your access pattern is not very least recently used friendly, it's maybe, for example, some blocks are frequently used. You may want to determine those frequently used blocks as opposed to recently used blocks. And these are two different things because recency is in time, frequency may be in a much longer time frame. Recency looks at what happened very recently, basically, right? Frequency may look at a much longer time frame in terms of how frequently you use the block. Okay. We're going to talk about some of these, but keep in mind that hybrid replacement policies are also possible because just like hybrid branch predictors, right? If you remember, when we designed branch predictors in lecture 16, 17, we said that different branches benefit from different algorithms for better predictability. Some branches are better predictable using local predictors. Some branches are better predictable using global predictors. Some branches are better predictable using perceptrons potentially. And some branches are easily predictable just with a single last time predictor. So we designed these heterogeneous or hybrid branch predictors. Similarly here, different cache blocks and different access patterns benefit from different management policies in caches. So having heterogeneous replacement policies actually enable you to do even better than a single policy that tries to do it all. And we're going to talk about the optimal replacement policy also. Okay, now let's go to, let's say, new slide. So we talked about LRU, and the idea in LRU, least recently used, is to evict the least recently accessed block. This is not just a replacement policy, actually. It's a management policy. It makes decisions in terms of insertion, replacement, as well as promotion. Right? So if you want to evict the least recently accessed block, you have, within a set, of course, you have to keep track of the order of accesses that have happened to those blocks that you have in the set. Right? You have to have a perfect ordering across those blocks. Because once you evict the least recently used block, some other block becomes the least recently used, right? And you have to keep track of that. Once you evict that, some other block is recently used. So you need to really have an ordering of the blocks. And this ordering becomes actually extremely hard to maintain, even with a four-way cache. Okay, basically that's the problem. So maybe I'll ask you the question. If you have a two-way associative cache, how many bits do you need to decide which way is the least recently used? Anybody? So, it's not a trick question, it's an easy one. Who says one? Yes, I think one, don't be shy. One is the right number, basically. Well, at least, of course, you can do with more, right? If you have two, you can do with more. Basically, there are two ways, and one of them is least recently used. The other must be the most recently used. And if you identify the least recently used one with one bit, saying way 0 or way 1 is the least recently used, then you can actually evict that one, right? And that basically is a complete ordering. Okay, maybe the trick question is, if you have a direct map cache, how do you implement LRU? That's tricky, because in a direct map cache, you hopefully know that you have no replacement decision to make, right? Because you have only one location to put a block into, and you either replace that block or not replace that block. That's a different decision. You're not choosing which block to replace. You're basically replacing or not replacing the block. Okay, so now if you go to four-way associative cache, the harder question is, what do you minimally need to implement LRU perfect? Basically, said in other words, what is the minimum number of bits do you need to encode the all possible different orderings across the 4 ways? Basically, how many different orderings are possible for the full blocks in the set? Okay, anybody? This is a harder one. The first one was easy. Now you need to think of it, right? You have four different ways. At any given point in time, if there's no answer, I'm going to answer. Yes? Exactly, 4 factorial. Can you tell us how? Exactly. Exactly. So if you want to think about it internally, this is basic probability theory, right? If you actually look at 4 possible blocks, there are 4 possible orderings. So way 0 can be one of those 4 blocks can be the least recently used. And once you decide least recently used, there are only 3 blocks left to be the next least recently used. And then once you decide that, there are only 2 blocks left to be the next least recently used. And once you decide that, there's only 1 block left to be the most recently used. So there are 4 possibilities in the first slot, 3 possibilities in the next slot, 2 possibilities in the third slot, and 1 possibility in the last slot. So you have a 4 factorial, 4 times 3 times 2 times 1, different possible orderings in which you can choose those blocks to be at those 4 possible positions. And that's what gives you the 4 factorial. Okay, once you have the 4 factorial, you can answer the second question. What do you minimally implement? What is the minimum number of bits do you need to implement LRU perfectly? That's log 2 to the 4, right? 2 to the 4 factorial. So 4 factorial is 24. Log 2 to the 24 is 5. Basically 5 bits, essentially. I'm correct, right? Okay. So now it's 5 bits. Of course, you can say that you can do with more bits, right? The 5 bits encodes the ordering. Now you need to decode the ordering also, right? Whenever you're trying to figure out which one's the least recently used, you have some 5-bit encoding. You need to decode that and figure out, okay, this is what this ordering says. Way 0 is the least recently used. Way 1 is the second least recently used. Way 2 is I don't know. Way 3 is third least recently used, and way 2 is most recently used. So every ordering, every encoding has a correspondence, and you need to decode it. So basically, that's part of the logic that's needed to determine the LRU victim in the end. And then you need to re-encode, right? Once you do the decoding and once you do the eviction, you need to bring the block into the evicted part, and that becomes the most recently used. So you need to re-encode these bits. So there's more logic to deal with this, which I'm kind of describing, but I'm not implementing. But implementing actually this takes a lot of effort in the end, and this is just a four-way associative cache. So we already answered this question, and I kind of answered what is the logic needed. So this becomes a bit cumbersome, basically. And we already said that LRU is not the best pattern, potentially. I'm going to show you more examples. There are patterns that are just not so friendly, that don't benefit from an LRU policy. So does it really make sense to implement LRU? So if you actually generalize this to n-way set associative, if n is, you get n factorial orderings, right? So if your associativity is 32, you get 32 factorial. That's a huge number. If your associativity, you want it to be 512, that's 512 factorial. So basically, keeping track of this ordering perfectly becomes infeasible. Even if you can do it for 4-way, soon you will not be able to do it. So that's why people try to do approximations to LRU or different policies in the end. Okay. So basically, that's the reason why most modern processors do not implement true LRU, also called perfect LRU, which keeps the ordering perfectly in highly associative caches. Well, we kind of said both of these basically. There are 2 reasons why. True LRU is complex, as we discussed. And also, LRU is not the best management policy anyway, to begin with. It's just an approximation to predict locality. So I will not talk about a lot of these examples, but and if you're really interested, you can take the advanced course or watch the materials that I mentioned later. There are some examples. Some processors use not most recently used, for example. It's kind of an approximation of LRU, but very easy to implement. You just keep track of the block that's most recently used and don't evict that. And among the other blocks that are in the set that are not most recently used, you pick a random choice. Right? That's very easy to implement. There are policies that have hierarchical LRU that divide n-way set into different groups and then track the MRU group and not MRU way in each group. So basically, you're trying to approximate LRU without being perfectly, without keeping track of a perfect ordering across blocks. And there's something called victim next victim that just looks at victim and next victim, which I'm not going to go into. And victim happens to be the least recently used in the end, as much as possible, but not necessarily. Okay. Okay, now let's take a look at, we kind of talked about the implementation aspects of LRU, but let's take a look at where LRU fails badly. If I ask you the question, LRU versus random, which one is better? I think we kind of discussed this. Let's take a look at a four-way cache where you have cyclic references to A, B, C, D, different blocks that go to the same set. And basically the behavior of the program is keep on accessing these in a cyclic manner, A, B, C, D, E, and then A, B, C, D, E again, A, B, C, D again, A, B, C, D again, A, B, C, D again. This is a, let's say, a pathological access pattern for LRU because you get a 0% hit rate, right? If you follow the strict LRU policy, you get 0% hit rate. You always evict the block that you're going to use, let's say, not next, but basically you don't have enough space. You don't have enough space to host these blocks and this access pattern in the cache. And this is called set trashing, basically. You have a program working set inside a set. We're looking at a set that is larger than the associativity, set associativity that you provide in the cache. Basically, you're trashing that set. But you can realize that you can manage this better also. Even though you're trashing the set, yes, you need 5 items there to be to really get 100% hit rate. You can do at least better than 0% hit rate if you do something other than LRU. LRU is actually the worst policy. I mean, there might be other worst policies also here, but LRU is the worst policy in this case. So random replacement policy is, for example, better when trashing occurs, right? You basically don't select the LRU. You say, I have 4 items, A, B, C, D. I'm going to randomly pick one to evict. And let's say your random choice was D. That's good, right? If you evicted D, hopefully you will, when you get to A, it'll be in the cache, right? Of course, random may actually give you a pathological pattern that looks like LRU also because random you're not controlling, but the likelihood of that is very low. So a random replacement policy actually keeps some of these blocks in the cache. Or another policy is you fill the cache A, B, C, D, you figure out that trashing occurs. At some point you say, I'm not going to evict anything. I'm happy with A, B, C, D in the cache, and whenever E comes, it always misses. That sounds good, right? For this access pattern, that's a good policy. It gives you 80% hit rate on this access pattern. So basically, locking the cache and saying, I'm not bringing anything else because I figured out that the set is trashing is a simple way of getting a very high hit rate, better than random, actually. Okay, you can calculate the random hit rate. For those of you who like probability and analysis, you can probably calculate the random, the hit rate that you would get with random, but it's not going to be 80%. Okay, so in practice, performance of the replacement policy depends on the workload, just like we discussed. And the average hit rate, this is actually a very interesting result. It was repeated multiple times. Average hit rate of LRU and random are similar across a wide variety of workloads. So LRU is not the best, random is not the best, and they're similar in terms of hit rate. So, but they cater to different workloads. That's the key realization. So if you want to really get the best of both worlds, you really want a hybrid policy. Again, LRU and random, or you become more intelligent like what we discussed. You keep track of the access patterns and figure out what's going on in each set and try to optimize for each set. That's a possibility also. But hybrid policies are relatively easy to implement. You may have each set, for example, implementing both LRU and random, and dynamically you decide which one to use. And you can basically do this by sampling sets. I'm not going to go into the details of exactly how this is done, but you can imagine, right? Dynamically, you figure out, you kind of emulate each policy and say, for this set, LRU is doing better. For this set is random, and random is not doing better. So I'm going to use LRU for this set and random for this other sets, for example. There are multiple ways of doing it. Of course, hardware cost becomes an issue also here. Very similar to hybrid branch prediction, right? For this branch, local branch predictor is doing better. For this other branch, global branch predictor is doing better. Okay, and we're going to talk about this paper in a little bit, but this paper is the first one to propose the sort of sampling approaches for hybrid policies like this. Okay, then people also ask the question, what is the optimal replacement policy? We're going to question this later on, but this is important to discuss. Of course, when you think about optimal, you should always think about what is the goal of the optimal, right? Because your definition of the policy may change if the goal is different. Here, we're going to assume that the goal is to minimize the miss rate or maximize the hit rate. And this person called Belady basically proposed this opt policy. And the idea is to, of course, it's not going to be implementable. Idea is to replace the block that's going to be referenced furthest into the future by the program. Then the question becomes, how do you figure that out, right? Because this requires knowledge of the future. And clearly the program is executing. Interestingly, people have tried actually very recent works. There are some recent works in literature that try to emulate this policy. They cannot do it perfectly, of course, because you don't know the future perfectly, but you can try to emulate it based on what you have seen in the past. Again, we're not going to go into that. But if you're interested, you can take a look at this original paper that discusses optimal policy. And a lot of these ideas were actually first discussed in virtual memory systems, which we're going to talk about next week. Because a lot of similar issues also happen in virtual memory systems, again, which you will see. The question is, you cannot implement this. Even simulation of this is hard, actually. If you want a challenge in software engineering, how do you simulate a policy like this? It's pure software engineering in the end, and also some thinking. If you don't do the right thing, those simulations may take like a really long time and require a lot of memory also, because you're really looking further in the program. Okay, so I think I already answered this question. This is really optimal for minimizing the miss rate, because you're really picking the block that's going to be referenced furthest into the future to evict. That minimizes the miss rate. You can also, again, read the paper or prove it to yourselves. But hopefully, it's clear that this is not necessarily optimal for minimizing the execution time. We've distinguished these two before. We're going to distinguish even more. Execution time is dependent on many, many factors, right? Not just miss rate. It is dependent on how long the latencies are, whether the latencies are overlapped, whether the processor is waiting for a miss. So you may have a miss from the cache that may take only 2 cycles, and the processor doesn't even stall for it because it gets hit. It hits somewhere else, let's say. I don't know. You may have another miss that takes, I don't know, 500 cycles, and the processor stalls. Okay, we're going to distinguish actually between these. So basically, the key takeaway is miss latency or cost varies from block to block. Latencies vary, and also how long, what is the effect of that miss on the processor varies depending on how much latency is tolerated by the processor. So we're going to see a very interesting example of this. So maybe I'll not go into detail. But there are multiple reasons for this. We're going to talk about the reasons also. For example, not all misses are equal, right? One cache miss from L1 can get service from L2. Another cache miss from L1 may have to go to remote memory. These are not equal misses, right? And if you actually count them as equal, yes, you're optimizing for miss rate, maybe hit rate, but that's not what your performance is bottlenecked by necessarily. Your performance is bottlenecked by not just miss rate, but also the cost of a miss, right? So always keep that in mind. Performance analysis is relatively complex. You cannot just say, oh, my cache miss rate is, let's say, 99%, and it's great. Depends on what 99% is hitting in the cache. Okay, so we're going to talk about this. And basically, maybe I'll mention this. This paper that we wrote a long time ago talks about some misses being costly than others, as their latency is exposed as stall time to the processor, but some other misses, their latencies are not exposed to the processor. So reducing miss rate is not always good for performance, actually. And I'm going to show you a real example of this soon. So the key takeaway is this cache management policy, not just the replacement policy. In this particular paper, we talk about replacement, but it's really about management. Cache management policy should really take into account the performance effects of the decisions, not just the hit rate or miss rate. Okay, now let's go into a little bit more basics. Feel free to interrupt me with questions. This is a fascinating topic. If you have an idea, probably it's been proposed by someone in the last, I don't know, 60 years. But people still come up with ideas. Don't let that discourage you, basically. There's huge body of work in an area like this, especially. There's a huge, amazing body of work in software and hardware, but people still come up with ideas that move the needle. Okay, so what's in a cache? Let's go back to some of the implementation issues of caches, because the tag store we discussed, right? We talked about val bit, tag bits. These are the minimum things you need. But you may also need replacement policy bits. We just discussed some of them, right? And LRU, for example, at least you need to have the encoding of the ordering. You can, of course, have more bits to make it to make the encoding and decoding simpler. So now we're making tag store bigger and bigger. So if you have a sophisticated replacement policy or management policy, you need to increase the size of your tag store. And this affects your access time to the caches as well, basically. Okay, so let's talk about something else, though. There's some other bit that you may need, depending on the decisions you make in your cache, related to stores or writes into the cache. Whenever you write to the cache, you modify the block in the cache, or and you may need to keep information about the fact that you modified the block in the cache. If you actually wrote to the cache and no other cache, this is the updated block in the cache, and you should know that. And a lot of other things in the system may need to know that also. So people actually propose to have this dirty bit, saying that this block is dirty or written to distinguish a block that's clean, meaning the copy of that block is the same as the copy in memory. You need this information because whenever you evict a block, you need to decide, do I write this block back into the next level? For a clean block, you don't need to, because the copy in the next level is the same as the copy you had. But if you actually modified the block, you need to write it back. So it's called a dirty, written to, or modified bit, basically. But this very much depends on how you handle the writes in the cache. And writes actually open up a lot of interesting design choices. Reads also open up a lot of interesting design choices we discussed, but let's talk about writes a little bit. So the question is basically this: when do you write the modified data in a cache to the next level in the hierarchy? Write through means that at the time write happens. Basically, whenever you write to this cache, you write to the next level also. That's a write through cache. You're really writing through the caches. That's why it's called write through. Write back means when the block is evicted. So you don't inform any other cache. You wait until this block is evicted, and then you write it back. So if you want to do a write back, well, that means that you need to have a dirty bit, basically, or modified bit per tag store entry. The benefit of write back, of course, is that you don't basically expose the next level of the caches to every single write that you're doing in the program. What does this mean? If you have a cache block, and if you keep writing to it many times, every single write doesn't go to the next level. Right? You basically combine these writes to the cache block. This is called write combining to the same block before it gets evicted. And this saves potentially a lot of bandwidth, right? Because you do one write to the next level as opposed to maybe a million writes if that block receives a million writes before it gets evicted. Right? And this actually is a huge benefit, clearly. Of course, the downside we already discussed. You need to keep track of this dirtiness or modifiedness. Write through is actually simpler design. You don't need that additional bit. There's another benefit though. Maybe you don't care about that additional bit, right? It's only one bit. We're already adding a lot of bits for replacement policy potentially. The benefit is all levels are up to date and consistent. Meaning, whenever you wrote to this L1 cache, you wrote to the L2 cache, L3 cache, L4 cache, maybe shared between processors. That means that some other processor, if it needs the block, can get it from another level. Right? So we're going to talk about cache coherence issues if you have time, briefly again. Have you seen this in another course, cache coherence? Probably in parallel programming, yes. So you kind of understand the concept of cache coherence. But basically, write-through caches simplify cache coherence. Some other processor doesn't need to access the L1 cache of another processor to actually get the modified data. They can basically access some other L4 cache, for example, that's shared between processors. And this may be simpler. But of course, the downside we already discussed. It's exactly opposite. The opposite of the upside of write back. It's a lot more bandwidth intensive. There's no combining of writes. Every single write goes to the next level. So you basically waste a lot of bandwidth, potentially. Energy as well as performance. Because whenever you're doing it to write to another level, you may be delaying reads at that level. So that affects your performance. Whenever you do a write to another level, you're exercising buses between the levels, wires between the levels, that's consuming energy. If you could save all of them and write back, why not? Okay, so existing caches actually usually are write back, but some levels may be write through, especially if the cache is small and they want to basically simplify the coherence so that the coherence domain doesn't extend to those caches. L1 caches sometimes may be write through actually. But in many cases, we have write back. So definitely You don't do write through to memory today, for example. That would be a terrible design choice. If you have an L4 cache, it's not a write through cache, it's a write back cache, because going to memory for every single write is extremely expensive. Okay, another question with writes. Do you allocate a cache block on a write miss? Whenever you, so okay, on the L1 cache, you get a store, for example. And the store misses in the cache, meaning there's no cache block associated with it. Do you bring the cache block into the cache and allocate it? I mean, same question exists for reads, actually. But writes are interesting because their locality may be different from reads. So you actually need to ask the same question for reads, but people have asked the same question, this question for writes first, interestingly. So if you allocate the cache block on a write miss, then the answer is yes over here to this question. If you don't allocate it, then the answer is no. So let's take a look at the trade-offs. If you allocate the cache block on a write miss, you can combine the writes instead of writing each individually to the next level. So there's, again, the combining effect, right? Combining effect. If you don't allocate, you keep writing to the next level. Right? Maybe not good. And this is simpler because write misses can be treated the same way as read misses. But of course, the downside is this requires a transfer of the whole cache block. This may not be good in some access patterns, right? For example, you're doing a random write, a 4-byte write. That's it. You're not going to use that block again, ever again. You're bringing 64 bytes. If you're unlucky, maybe 256 bytes, if your block size is 256 bytes, to the cache, just to do a 4-byte write. In that access pattern, that's not a good design choice, right? So basically, design choices very much depend on the access patterns, as you can see. If you can somehow determine your access pattern, either in hardware or somebody tells you from the software level, you can actually make your management policies much, 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 much better. At the cost of complexity, of course, right? Okay, no allocate means that you don't allocate on a write miss. Of course, this conserves cache space in the access pattern that I just discussed, right? And also bandwidth, because bringing a 64-byte block consumes bandwidth from memory, and also cache space because it'll be allocated. Right? Okay, if the locality of written blocks is low, as we just discussed, right? So you get potentially better cache hit rate. So the decisions in the end very much depend. A lot of the caches today are allocated on write miss, but a lot of caching decisions today are also very much trying to guess the access patterns in some way. So both for reads and writes, they may not allocate blocks. Okay, another question with writes. Writes are kind of interesting. What if the processor writes to an entire block over a small amount of time in a streaming manner? What does this mean? Well, maybe, let me ask the next question first. Is there any need to bring the block into the cache from memory in the first place? So assume an access pattern where you're writing into a block, maybe the earlier access pattern, and you're never going to use that block again. You just write to that block and reads are not going to reference that block because you're going to store it to memory and forget about it for a while. Can you somehow do better in this case? Right? So people have developed the idea of sub-blocked or sectored caches. Why don't we simply write to a portion of the block as opposed to the entire block? And this is called a sub-block, basically. For example, if your writes are if you're doing a 4-byte write out of 64-byte write to that 4-byte and validate only that portion. The remaining 60 bytes will be invalid. So now you need to have partial valid bits for different parts of the block. Now, the good thing is a lot of programs may do what's called streaming writes. So you start from the beginning of the block, write 4 bytes, and then write the next 4 bytes, next 4 bytes, next 4 bytes, next 4 bytes, until you write 64 bytes. If you have an access pattern like this, you don't ever need to bring the cache block again. You don't ever need to bring the cache block. You just form the cache block inside the cache, right? The entire cache block becomes validated in the cache because the processor writes to different sub-blocks. Makes sense, right? So you never need to bring the old version of the cache block because it's going to be written completely anyways. Okay, so basically, sub-blocking requires some additional hardware. Valid and dirty bits are associated with the entire 64 bytes, as we have seen so far, not with individual 4 bytes or 8 bytes, whatever your write granularity is. So to fix that, we need to have a cache that kind of looks like this. Divide a block into sub-blocks. This is also called sectors, an old idea. Have separate valid and dirty bits for each sub-block or sector, but a single tag bit, a single tag for all of them, because they share the tag, right? They're still the same. They're still parts of the same cache block. And we allocate only a sub-block or a subset of subblocks on a request. So this kind of gives you some more design freedom as well, right? So yes, you have these additional valid and dirty bits, 16 of them, if you actually have 4-byte subblocks and a 64-block cache. But now you can decide, I'm going to allocate only this subblock. Or, and you can, for writes, clearly this could be useful. For reads, this could be useful also, as we will see. So basically, the key takeaway is there's no need to transfer the entire cache block into the cache. You can transfer only portions. Or if you're writing, you can write only to a subblock. And a write simply validates and updates a subblock. There's no need to transfer anything in the case of write. Now you have more freedom in transferring the subblocks into the cache. A cache block does not need to be in the cache fully. Subblock 1, subblock 5, subblock 13 can be in the cache, right? And if you're even more sophisticated, if you can predict which subblocks are going to be useful in your cache, you can fetch only those subblocks from the next level in the memory hierarchy. So this can actually save a lot of bandwidth, not just write bandwidth, but read bandwidth. Whenever you request a cache block, you have a predictor that tells, oh, in the past, I really needed subblocks 1, 5, 7. Only get those for me from the next level of the hierarchy. This can save, so how much bandwidth do you save in that case? You're bringing 3 subblocks instead of 16 subblocks, right? That's essentially a lot of bandwidth savings. Okay, so of course, the trade-off is more complexity, right? Now you need to figure out which subblock do you transfer? How many subblocks do you transfer? It's going to be easy to predict them. What if you mispredict? You said, I want subblock 1, 3, 7, but later the processor asked for subblock 15. Well, too bad. The processor misses on the subblock. So you get a cache miss, even though you could have brought some more, right? So these are things that basically keep cache designers up at night. Of course, the downside now is more complex design, right? At the very least, you need the valid and dirty bits per subblock as opposed to per block. Tag size doesn't change. That's the good part, because it still refers to that 64-byte entity. And you need to figure out like when to validate different parts of this block. And this may not exploit spatial locality fully clearly, right? Because you're not bringing the entire block into the cache first. Okay, so sector caches exist in real life also. We discussed this in the last lecture, but I want to have a formal slide on it also. Do you want separate or unified instruction and data caches? And again, this is a design decision. If you unify the instructions and data, you get dynamic sharing of cache space. No over-provisioning that might happen with static partitioning. So for example, you have 128 kilobytes of space for instruction and data caches, L1 caches, let's say. If you divide them into 64 kilobyte caches, this may not be good for sharing, space sharing, right? If your instructions working set size is only 1 kilobyte, you're underutilizing the 64 kilobyte instruction cache. If your data working set size is 127 kilobytes, you basically need more space in the data cache, but you don't have it, but you have it in the instruction cache because the instructions are not utilizing it. So separating the storage for instruction and data clearly leads to this static partitioning. But if you actually unify them, you have dynamic partitioning. So this is actually always true. You can actually change the instruction and data to core 1 and core 2, for example. Different cores may share their data caches, for example. And again, you have the same trade-off. Dynamic sharing enables higher hit rates in general. But of course, unified has a problem. Instruction and data can evict each other, right? So no guaranteed space for either one, basically. It's unless you manage it in some way, which we may talk about at the end of the lecture. But most importantly, in a pipeline design, as we discussed also last time, instructions and data are accessed in different places in the pipeline. Instructions are in the fetch state. Data is accessed after the loads are scheduled, right? So there's a huge distance actually in the real chip implementation. As a result, if you really want to have a unified cache, there's no good place to place it, basically. It's better to separate these caches. So basically, as a result of especially the last one over here, the other ones are important, but this last one is the key thing that constrains the design decision. First level caches, L1 caches, are almost always split because of the pipeline constraints. But higher level caches, like outer level caches, maybe I should call these outer level caches. Actually, I like outer level better. Let's correct that. because inner means closer to the CPU, outer means far away from the processing units. Okay, outer level caches are almost always unified. Now there are some exceptions. There were some cases where people had L2 instruction, L2 data caches also in the past, but yeah, it's not that common anymore. Okay, so this brings me to multi-level caching in a pipeline design. Basically, first level caches, instruction and data are design decisions that you have in first level caches are very much affected by the cycle time and the pipeline structure. So they're usually small, lower associativity, and latency is critical because you want to get the data quickly into the pipeline so that you don't stall much. And tag store and data store usually accessed in parallel. Second level and later level caches, design decisions are more relaxed from the pipeline, let's say. So you actually, not as much latency dominated, let's put it that way. And also location dominated in your chip. As a result, decisions need to balance hit rate and access latency. And these are usually large and highly associative. Latency, not as important. Don't forget the not over there. Don't forget the as over there. Basically, it's not important, not as important as the first level caches, right? So one design decision, for example, in second level or third level caches is, do you access the tag store and data store in parallel? Whenever you index the tag store, do you also index the data store? Or do you wait for the tags access to complete and you get a decision on hit or miss and which way to hit or miss before you index the data store? In the later level caches, outer level caches, you may actually access the tag store and data store serially because these are highly associative. First of all, it could be 64-way associative. And you may actually, whenever you miss in the data store, miss in the cache, it doesn't make sense to have activated all those 64 ways. So remember, data store accesses all of the ways, brings all of the data, and then based on the tag store hit or miss status, you decide which data to use. If you miss, you don't use any of the data. If you hit, you use only one of the data, 1 out of 64, if it's 64 ways. So it's a lot of energy to fire up these huge memory array structures so that you can use either 0 or 1 of the blocks. That's why people try to do this serially, especially farther away from the cores. Right? So what does serial mean? You access the tag store. Tag store gives you a hit or miss. If it's a miss, you don't access the data store. You saved a lot of energy, and you didn't impact latency at all. If you hit, the tag store gives you which way you hit. So you don't access all of the 64 ways. You access the way that you hit on. As a result, you actually save 1/64. You actually say 63 out of 63 divided by 64 of the energy that you had on the data store. Of course, this incurs a little bit additional latency because it's serial access. But hopefully you can tolerate it with some other way. Okay, there's also the design decision of serial versus parallel access of levels. Serial means second level cache is accessed only if the first level misses. Or do you start the access in parallel while you're accessing the first level? So if you start the access in parallel, if you start the first level access and second level access in parallel, if the first level misses, then second level access completes quickly. Of course, the downside is always energy in these things, right? That's the downside. So you should be very energy conscious when you design these things. Usually, levels are accessed serially today. You don't do parallel accesses. As a result of this design decision, especially due to energy and also complexity, second level doesn't see the same access as the first. And third level doesn't see the same access as the second level. Fourth level doesn't see the same access as the third level. And memory doesn't see the same accesses as the fourth level. Which means that L1 caches see all the accesses coming from the processor. So they can actually understand the access patterns much better. The access pattern that goes to the L2 cache is filtered by L1. And it keeps getting filtered as you go to memory. So basically, it filters, the first level filters some temporal and spatial locality. This affects the management policies a lot. This is why management policies at the level 1 should be different from the management policies at level 2, not just because of the pipelining structure. Right? So as you go farther from the processor, your management policies become even more different. And then there are other aspects, like these caches farther away from the processor, caches may be shared by other processors also. So your access patterns become even more complicated. It's not just about this particular processor. So this is also very important to keep in mind. L1, you don't have a lot of flexibility, but L2, L3, L4, when you get to it, management policies become very different. They need to take into account this filtering effect. So I'm going to show you some more pictures, as you have seen. So clearly, this is actually interesting because people don't show the caching structures, but they occupy a lot of space. So here's a cache here, L2 cache. GPU, they don't even talk about caches in this case, as you can see. System level cache. So there are many, many caches actually over here, and some scratch pads in the neural engine, I bet. So this is Intel's. Intel's actually very good at optimizing the area of SRAM caches. That's why their caches are much smaller than others, even though this is an approximation. But again, there are a lot of caches everywhere. So there are some caches over here for the small cores, for example, GPUs, etc. So this is AMD. And more recently, AMD, this is a huge cache, as you can see, L3 cache, 32 megabytes shared. But even that was not enough, especially for gaming CPUs. They introduced this 3D stacking cache. So on top of this processor with 32 megabyte cache, you can actually stack another, let's say, I don't want to call it the processor, but another layer that just has an L3 cache, 64 megabytes. So you can get 96 megabyte cache. So these caches are growing, as you can see. This may also, if you're a critical thinker, maybe you should say, is this really the right way of designing things? Right? There's a lot of interesting performance analysis on this cache, actually. It does improve performance on some games, but may not on some others. So this is the 20 megabytes cache in Power 10 IBM. Huge, as you can see. And we're just talking about L3 over here. L2 cache. People don't even talk about L1 caches these days because they're so small and they're so tightly coupled with the cores. Okay, these are GPUs, and these are more recent GPUs. Even their cache sizes are growing, as you can see. And the management policies are also different. So I will cover this slide and the next slide, and then we're going to take a break. But this is interesting because this is NVIDIA V100 and A100 GPU. Management policies of the hierarchy, programmers can have freedom in their management. So, okay, maybe I'll go back here. We mentioned this last time, but here, for example, L1 caches can be used as either caches, hardware managed caches, or scratchpad, programmer's choice. If the programmer thinks they can manage the cache better, they will manage the cache as a scratchpad. It's not a cache anymore because it's not automatically managed, right? But L2 cache is always automatically managed, as you can see. Okay, but there are other design decisions. For example, this A100 has a feature where you can directly copy from L2 to scratchpad. You can bypass the L1 and register file, for example. So these things can get exposed to the programmers, especially in GPUs where people who program these things may have actually a lot of experience. They may benefit from this sort of exposure of the memory hierarchy using instructions so that they can actually decide where to place the data, right? In general purpose processors, these instructions also exist, but they're more like hints. The programmer can say, okay, I don't want to place this data into this cache, and they have some limited control, not perfect control. But the processor, there's no guarantee basically. The processor can say, okay, I'm going to ignore what you said. And this happens in a lot of the cases actually in general purpose processors. But GPUs, because there's a scratchpad means that it's another level in the memory hierarchy. It's not automatically managed. So the GPU cannot say, I ignore you. Well, if it says, then the programmer can figure it out easily, right? And the programs will be wrong. Okay, so this is actually a more recent NVIDIA GPU. This is just to show you there's a lot of stuff that you can do, like directly copy from the main memory to the scratchpad. As we discussed, shared memory is not a great name for it, but they like using it. You can do a streaming multiprocessor to streaming multiprocessor copy across the scratchpads, programmer controlled. And you can see the sizes are quite large, right? And the bandwidth is quite large also. So let's go over the slide and then we're going to take a break. Basically, multi-level cache design decisions. We have design decisions in every single cache, but also across the hierarchy. And these examples show you that design decisions actually cross the hierarchy, right? And these design decisions may be controlled by the hardware or the software or in a cooperative manner. And there's a lot of interesting proposals for doing it cooperatively. If you have a lot of information at the high level, it may make sense to actually bring it to the hardware, and the hardware also taking into account the dynamic behavior of the blocks can actually make a better decision. For example, which level do you place a block into from memory? Do you place it into L1, L2, L3, L4, all of them, a subset of them? You can see even that is a design space decision. Which level do you evict a block to from an inner level? Do you evict to all of the ones, or do you evict to directly memory? And there are many design decisions over here. Do you bypass some levels, not bypass some levels? And then there's inclusion, exclusion, non-inclusion of the hierarchy levels. Inclusive means that a block in an inner level is always included also in an outer level. Basically, there's redundancy in the levels. This L1 is a subset of L2, L2 is a subset of L3, L3 is a subset of L4. Of course, you can change the Not all of them have to be inclusive with respect to the next level, right? This simplifies cache coherence. That's the upside, actually, because you can check only the sum of the levels. You can actually replicate the tag stores, which we're not going to go into. Exclusive means that a block in an inner level does not exist in the outer level. So redundancy is minimized in exclusive hierarchy. It better utilizes space in the entire hierarchy. But this is more complex. This makes coherence complex, but also whenever you're evicting a block, you need to make sure that, or bringing a block, you need to make sure that that block doesn't exist anywhere else, right? And non-inclusive means that a block in an inner level may or may not be included in an outer level. And this also exists. A lot of Intel processors are non-inclusive, for example. It gets the benefits of neither, but it relaxes the design decisions. So you don't worry about this, basically. You don't worry about including. You don't worry about excluding. You basically say, I may include, I may exclude, and it's easy for me to design as a designer. Okay, so this is a good place to take a break at this point. Let's be back at 10 minutes later. So it's going to be 5 minutes after the bell. And we're going to talk more about cache performance. What happened? I think so. What do you think?
I have a question.
Yeah.
About citations in general.
Yeah.
So
Okay, I think we can get started. So basically, this is where, this is the last slide we covered. I'll mention that, don't forget this. Basically, a level doesn't exist in isolation. This is what slide is trying to tell you. It exists with many, many other levels. So it's really important to design the complete hierarchy in a holistic manner. Not all of that is necessarily happening, let's say, in existing systems, because if you, for example, go to a company, usually there's someone responsible for the core. They also take care of the L1 cache. L2 cache is, let's say, a little bit outside the core. These days, they're getting closer to the core also. It's no man's territory, let's say. But L3 cache is on core. Basically, someone else does it. And then memory controller, someone else does it. So there's also the human aspects of design that makes it difficult to really completely well manage the hierarchy, because they define interfaces between the levels, and those interfaces may not be good enough to communicate information across the different levels. And information at one level may not be communicated to the other level or may not be available. And as a result, a lot of the decisions at the memory hierarchy may be repeated or lost at different levels. But again, there's a research that shows that if you can more holistically manage this memory hierarchy, especially with semantic information from the program, you can actually do much better. So, but the management of this is perhaps the most important thing that you have for improving performance and efficiency. Because as we discussed in the lectures where we motivated the memory hierarchy and memory, we said that most of the energy spent on memory, most of the performance losses due to memory, most of your area, chip area is clearly, as we have seen in the pictures, is due to memory. Even then, we probably are not doing a good job in it, as we should. Okay, so let's do the performance analysis. And this performance analysis is going to be more like an individual level type of analysis, because it's important to study individual levels also. And we're going to look at different cache parameters versus the miss and hit rates. We're going to look at especially cache size, block size, and associativity, but clearly replacement policy, insertion policy, and promotion policy, the three policies basically have also effect, but we don't have time to talk about that. I'll mention one as we discussed earlier. Cache size is a biggie, of course, right? Cache size usually, well, almost always refers to total data capacity. So when people say 120 megabyte cache, they're talking about the data store size, not the tag store. Tag store is in addition to that. It has to be there, of course. Usually bigger caches can exploit temporal locality better, right? But not always better, because as you keep increasing cache size, your performance may not increase after some point. Why? Because your cache size may be enough to hold your whole working set, basically, because you're not going to touch more data, right? At that point, your cache hit rate may not increase. Or your cache hit rate may not increase because you've captured all of the temporal locality, and even though you need, you touch more data, that's more random access. It doesn't benefit from the larger cache space, for example. So this picture here, again, aggregated over many, many workloads, has cache size on the x-axis and hit rate, cache hit rate on the y-axis. And you can see that there are diminishing returns. Again, individual workloads behave very differently. I will show you in the next slide, actually. And basically, when the working set or the data that you're touching at a given time interval fits in the cache, then your hit rate maximizes and you get to the diminishing return space after that. Okay, so basically too large of a cache adversely affects hit and miss latency. So bigger is slower, which is not taken into account in the hit rate clearly. This is hit rate doesn't take into account latency clearly. So keep that in mind. Bigger is slower is always there. Too small a cache does not employ temporal locality well. Useful data is replaced often. As a result, your hit rate reduces when you go to too small cache sizes. Right? And working set, just to define it, is the entire set of data the executing application references. It could be instructions also. I'm using data in the more general sense over here, within a time interval, basically. And once your working set fits in the cache, you're exploiting all of the temporal locality you can exploit, and the spatial locality also, right? Because assuming that your cache set fits your entire working set in that case. Okay, so let's take a look at this from real data. Basically, benefits of larger caches widely varies across different applications. I'm going to show you 3 different applications. One application happens to be a streaming application. So x-axis is maximum cache is one megabyte L2 cache, and we allocate different ways from it: 1-way, 2-way, 3-way, up to 16-way. So here you have a very small cache size, 1-way. Here you have 16 ways, meaning the entire 1 megabyte. This is 1 megabyte divided by 16. But the performance, meaning misses per 1,000 instruction, that's the miss rate in this particular case, doesn't change that much, right? Basically, this is more cache insensitive or low utility from caching application. Another application that benefits a lot from the caching that looks like this, right? This high utility. As you keep adding cache, your miss rate reduces. Another application has more saturating utility. If you look at this, it gets almost zero hit rate, miss rate, very quickly, because at some point, very soon here, for example, it starts fitting in the cache. So you can see that different applications behave differently, and you can actually get a 0%, close to 0% miss rate. But not all applications benefit from caching. And this is just miss rate. Performance may actually become worse as you increase the size of the cache, because you're not benefiting from cache, but your latencies are increasing, potentially. Okay, so good to keep that in mind, basically. But basically, things vary. Even though I'm giving you average across many applications, different applications behave very differently. Okay, block size. Block size is the data that's associated with an address tag, right? That's the cache block size. You may have 2 small blocks and 2 large blocks, and the curve looks like this, as you can see. I'm assuming here that the cache size is constant. You keep the cache size constant, do you have small blocks or large blocks, basically? But this is not necessarily, just to, before we study this, this is not necessarily the unit of transfer between the caches. Because unit of transfer between the caches can be at a sub-block level, sub-block granularity, smaller than the block size, basically. And that's actually true in many cases in existing hierarchies. The unit of transfer between L1 and L2 is larger. As you go from L2 to L3, it's smaller. L3 to L4, it's smaller. Once you go from last level cache on chip to memory, it's even smaller, around 64 bits, for example, in a given cycle, let's say. Okay, sub-blocking clearly helps this. So if you have 2 small blocks, your hit rate is low, as you can see. If you have 2 large blocks, your hit rate also becomes low. Why? Because 2 small blocks clearly don't exploit spatial locality well. That reduces your hit rate if you have a lot of good spatial locality. But they also have larger tag overhead, which is not reflected over here clearly in the hit rate. 2 large blocks, assuming the same size cache, you don't change the size of the cache, lead to too few total blocks, right? If your cache size is 1 megabyte, if your block size is 1 megabyte, you have 1 block in the cache, right? As a result, you may not exploit temporal locality well, right? You may exploit spatial locality only for 1 block also. As a result, your performance degrades, as you can see over here. So there's a sweet spot on average, again, across many applications. So 2 large blocks also waste cache space and bandwidth and energy if spatial locality is not high. Imagine that you're accessing only 1 byte out of the 1 megabyte block. You wasted your entire cache space, essentially, right? Okay, so large blocks, essentially large blocks, there are some issues with large blocks. People have tried to increase the block size, and they always run into these issues. So 64-byte cache block in IBM 370 is still 64 bytes today in many cases. There are some cases where you have 128, 256 bytes, but that's probably the largest. So one of the reasons is large cache blocks can take a long time to fill into the cache. Right? You have 256 bytes, and your bus on the memory side is 8 bytes. So it takes 32 I/O cycles from memory, DRAM cycles, right? And also they can waste bus bandwidth, as we discussed, right? So people have developed ideas to alleviate this. For example, fill the cache block with the critical word first. So a critical word is the word that's requested by the processor, the load, for example, that you're loading from. Supply this critical data to the processor immediately with a very fast path and fill the cache later. So a cache fill takes, I don't know, very long time, but supply the critical word as soon as possible. This requires the communication of what is the critical word from the processor all the way down to the memory controller, right? So there's some communication that you need to do if you really want to do that, because critical word may not be the first word you access from memory. Cache block is 64 bytes. It could be anywhere within that 64 bytes. Okay, we discussed this. Large cache blocks can waste bus bandwidth, but with sub-blocking, you can reduce this, right? And we discussed, for example, instead of bringing the entire 64-byte block, bring 4-byte sub-blocks at a time. And decide which 4-byte sub-blocks to bring. And if you do your prediction well, this could be very, very useful. And for writes, streaming writes, actually, it's a very good idea. Okay, So large blocks are interesting to handle. This is one of these are two reasons why people are not increasing the size of the blocks. Plus, there are other reasons that we discussed on this slide over here. Okay, and then there's associativity, which we discussed actually. So I'll go through this relatively quickly. If you have larger associativity, you get usually lower miss rate, not always, because at some point you don't need more associativity, right? Your conflict misses within that set is not growing. But you also get higher hit latency and higher area cost. So there are always downsides. Smaller associativity is lower cost and you get lower hit latency, but you can see that the hit rate is also lower, especially with direct map caches. Direct map caches are especially problematic because you have no choice basically. You have to place that block only in one place. You have no freedom in placement. Okay, so maybe here's not a trick question, but question. Do you need a power of 2 associativity in caches? Can you have a 3-way associative cache? 7-way associative cache? 17-way associative cache? Anybody? Or does it have to be powers of 2? Maybe this should be a good exam question, since no one is answering. But I have the answer in the next slide. Anybody? I know some people are shy. Okay, then I'll give you the answer. So this is 4-way. Maybe you can look at this and tell me whether 3-way is possible. So what is needed in a 4-way, right? You basically compare, and then you have a multiplexer to get the data out, right? So you need to compare the tags of all of the ways in a set, determine the hit signal, and then multiplex the data out. So based on this, is a 3-way possible? Or 17-way? Why not, right? This is the 3-way cache. I just remove the 4th way, and I have only 3 comparators. And yes, I still have a 4-to-1 mux, but I don't use this part, right? Basically, you just don't use part of the mux because mux requires a power of 2 to 1, right? Okay, similarly, fully associative cache, this is 8-way, this is 7-way. Again, you don't use this part. You could also have 6-way. You could also have 5-way that could do this, right? So basically, there's nothing in the address space because the reason is this is content associative search, right? Within a set, you're doing content associative search. There's nothing that requires an address to be a power of 2, for example. You're just searching the content and deciding which one matches, which one doesn't match. It could be an arbitrary number that you're searching, as long as you select the right one with the structures that we have built. Okay. So that brings me to classification of cache misses, which we kind of also discussed, especially the conflict misses, right? But there are also other cache misses. There's something that's not here, which is the coherence misses, which is essentially due to coherence. But I'm not going to discuss that right now. If you look at a single processor, your miss can be compulsory, capacity, or conflict from a cache's perspective. Compulsory means that this is the first reference to a block, and this is the first time the cache is seeing this block. This has to be a miss, clearly, right? This always results in a miss, essentially. And subsequent references should hit unless the cache block is displaced for one of the reasons below, right? So the first time you touch a block, it's always a miss because you haven't seen the block yet. And caching cannot, essentially, the definition of caching is you should see the block one time. Otherwise, you're prefetching the block into the cache, right? Okay, capacity miss means cache is too small to hold all the needed data. And this is more formally defined as the misses that would occur even in a fully associative cache with optimal replacement, which is very hard to implement clearly, of the same capacity. Right? Basically, we're trying to eliminate the reason of conflict. So that's capacity miss. And conflict miss is everything else, basically, neither compulsory nor capacity. You would get this miss because you're set associative and you're not running out of capacity, essentially. Okay, does this make sense? And this, I mean, this could be useful classification so that you can decide what to focus your efforts on. Not necessarily, let's say, hugely useful today, but it's good to know, for example, compulsory. Eliminating compulsory misses cannot happen with a larger cache. You could make your cache huge. I don't know, your cache may be 1 terabyte. If you're randomly accessing all of the data, your cache is always 0% hit rate, right? Because all of the misses are compulsory if you're truly randomly accessing all of the data. There's no locality, basically, spatial or temporal. Okay, so how do you reduce each mistype? Let's talk about this. Compulsory caching only access data cannot help, but increasing your block size can help potentially, because increasing the block size is really having a prefetching effect, right? If you think about it. Okay. Prefetching definitely helps, right? Anticipate which blocks will be needed soon and bring them into the cache before the processor needs them. So I have a predictor for this purpose. We're going to talk about prefetching hopefully in the next lecture, at least briefly. But this is actually required today. All modern processors have very sophisticated prefetchers. They're trying to be very, very clever in predicting the access patterns, and they try to bring the data, a block into a cache before the processor actually requests it. And that eliminates compulsory misses clearly. If you're doing a good job, you eliminate a lot of compulsory misses. Otherwise, caching is not useful for that. Conflict misses, more associativity can help. There are other ways to get more associativity without making the cache heavily associative, let's say. We're not going to talk about this. It's actually fascinating. A lot of people looked at this, and they try to minimize the overhead of associativity. For example, let me give you an idea. This is called poor man's associative cache, or pseudo-associativity. The idea is to have associativity in time, not space. The way we looked at associativity here is in space, right? This is fully associative cache. So you search for all the blocks in space at the same time. So the time-space duality also exists here. But you can do the search in time also, right? You can have a direct map cache, and the first time you access a cache block, you use one indexing function. You check whether the block in the cache. If it's in the cache, that's good hit. If it's not in the cache, you change your indexing function, access the direct map cache again. Now you hopefully map to some other possible place in the cache and check the tag. If it exists, that's great. You found it. If it doesn't exist, you do it again. One more time. Change the indexing function into the cache and then access some other block in another cycle, of course. And if it hits, that's great. Now you can basically search the entire cache. You can make the cache fully associative that way, right? In time. The downside is, of course, the associative search that you're doing is happening in time by changing the index function, of course. And the latency is very high. Here, the latency is one cycle, okay, whatever cycles it takes to do this comparison, but very quick because everything is happening in parallel. But the cost is very high because your space overhead is very high. You're doing the search in space, not in time. And you can, of course, have a combination of this, clearly, right? So basically, you can actually do things in space and time, and it's always good to think about this. But people have also proposed other things like victim caches, a small structure that keeps track of evicted caches, evicted cache blocks, so that maybe you're going to access them again. This helps direct map caches significantly, actually. And better indexing into the cache so that you can better utilize the indices sets so that you don't have very hot sets, for example, that you heavily do thrashing on. And software hints for eviction replacement proportion are actually quite interesting also. So software can, for example, say, I'm not going to use this block anymore. Don't cache it, right? Or software can say, I'm going to use these 3 blocks soon. So keep them in the cache. Right? So there could be hints like this. Capacity misses, utilizing cache space better helps. Keep the blocks that will be referenced. Again, here software helps a lot. And software management of the cache actually helps a lot. We're going to talk about that actually. Divide the working set and computation such that each computation phase fits into the cache. Because the way you wrote your program, you may require, let's say, much larger data than it could fit into your cache. But if you restructure your program, at any given point in time, the data that you need may fit in the cache. Right? So if you actually restructure your programs, you can get much higher performance in existing systems. Okay, so let's talk about some of those things. So if you want to improve cache performance, and in general memory hierarchy performance, but we're looking at, again, a single cache level, let's say, you can reduce the miss rate, you can reduce the miss latency or miss cost, or you can reduce the hit latency or hit cost. And these are all valid ways of improving performance, but unfortunately, they're interrelated to each other. So doing one may hurt the other one, let's say. So reducing the miss rate can reduce performance if more costly to refetch blocks are evicted. Reducing the miss rate may actually increase the hit latency by increasing the size of the cache, etc. So basically, all of the above together affect the performance, especially miss rate and miss latency a lot. Hit latency is especially important at the L1 level, and if you cannot really tolerate the latency. So people have proposed, as I said, over 60 plus years, many techniques. I'm not going to cover all of those techniques, but I'm going to give you some examples. So you can reduce the miss rate, reduce miss latency cost. I'm not talking about hit latency and hit rate because that goes into design of the caches a lot. So there are some examples over here. Let's talk about software approaches for miss rate reduction first, and then we're going to talk about better replacement and insertion policies quickly again for reducing miss latency and cost. Software approaches are interesting because these are things that you can do as a programmer, right? If you know what's going on in your memory hierarchy or what it looks like, at least some parts. If you go deeper and deeper to the memory hierarchy, you can optimize even more. And these usually require restructuring your data access patterns and also computation patterns, because computation is related to data access. You may need to rethink your algorithms, for example, and restructuring data layout. So there's some of these can be done automatically by compilers if you have a really good compiler. Loop interchange, data structure separation and merging, blocking, or tiling. You may have heard of this. Has anyone heard of cache tiling, cache blocking? No, okay, you have not done it in parallel programming, for example. But this is really critical for getting high performance. And I will show you an example of it, a high-level example. You can see the code examples. Actually, Juan teaches a course on heterogeneous systems where he covers a lot of these optimizations. So if you want to learn more about it, I'll recommend that course. Okay, so the key, let's take a look at restructuring data access patterns, and then we're going to look at data partitioning also, or data structure partitioning. So the idea over here is to restructure the data layout or the access patterns. This is best understood with an example. So we've seen matrices, for example, right? You may have a column major order. In this matrix, if you have a column major order, xi plus 1, comma j follows xi, comma j, that element in memory. Whereas xi, comma j plus 1 is far away from xij because of the way the matrix is laid out in memory, column major, right? Consecutive rows are in consecutive places, and the same column is like that. So this is very poor code. If you know this, you don't write this code. Why? What this code does is in the inner loop, it iterates through columns, meaning you access xi, comma j first, and then I, comma j plus 1 next, I, comma j plus 2 next, I, comma j plus 3 next. Basically, what I said over here, you're exercising this. xi, comma j, I, comma j plus 1, I, comma j plus 2, they're not in the same cache block. Everything that you do here is a cache miss. And actually, really, literally everything you do can be a cache miss in this particular case if your cache capacity is not enough, right? But the solution is very simple in this particular case. If you have this column major, let's say layout, you interchange the loops, meaning you do the traversal, inner loop traverses rows as opposed to columns, because now what your access pattern looks like xi, comma j, I plus 1, comma j, I plus 2, comma j, and they're hopefully in the same cache block. They should be, because that's how you lay them out. That's the idea. And this is called loop interchange. Again, if you're conscious as a programmer, you will do it, hopefully. Right? There are other optimizations that can also increase loop rate. You can fuse loops, for example. There are two different loops that are iterating through, let's say, the same thing. You can fuse them potentially to reduce miss rate. You can merge the arrays, etc. But we don't have time to go over a lot of these. Let's talk about blocking. Blocking also restructures data access patterns. Basically, the idea is also very simple. Divide the loops operating on arrays into computation chunks so that each chunk can hold its data in the cache. Caches of limited size don't overflow the cache, basically. Divide your computation such that it operates on data chunks that can fit in your cache. That's the idea. There are multiple ways of doing it. I'm going to give you one example. So clearly, this avoids cache conflicts between different chunks of computation and also avoids capacity misses for that chunk. Right? Yeah, essentially, you divide the working set such that each piece fits in the cache at a given time. This is also called tiling. So let's take a look at an example from GPU computing. Again, as I said, if you want to learn more about it, you can look at Juan's course. Same memory locations are accessed by neighboring threads over here. And if you want to take advantage of data reuse, you divide the input into tiles that can be loaded into shared memory. Again, scratchpad memory. So let's take a look at an example. This is how you do it. Again, I'm not going to go through the code over here. You can watch this GPU programming lecture. But let's take a look at, as long as this portion, for example. So here, for example, you're doing some filtering operation, right? So you have a Gaussian filter applied on every pixel of an image. This entire image may not fit in the cache. but this portion may fit. So apply the filter on this portion first so that you can exploit locality, and then move to the next portion, and then move to the next portion, and then move to the next portion. Don't try to do it in the entire image, right? That's the idea, basically. Because if you do it in the entire image, at some point you'll get cache misses, and then you'll go back, you'll get cache misses, and then you'll go back, and then you'll get cache misses. Whereas if you do the filtering only on this portion first, it will stay in your cache, you'll exploit the locality over there, and then move on to complete different portion. Yes, moving on to complete different portion will lead you to cache misses, but there will not be conflicts between the two different portions because you will not be going back and forth between them. Right? That's the idea over here. And this is how you do it over here. Again, I will not go through the code. Matrix multiplication is another example, right? You have two input matrices, A and B, and the output matrix is C. These all may be together much larger than your cache. Right? So naive implementation that goes through one row, one entire row of A, and an entire column of B to compute a point over here may have poor locality because you basically trash the cache as you keep going through the entire matrices. And also there are other issues like consecutive access to B are far away from each other in different cache lines. Every access to B is likely to cause a cache miss over here, right? Depending on the layout, of course. In this case, we're assuming row major layout. That's why this going through the columns actually lead to cache misses. So basically, you can achieve better locality by computing on smaller tiles. And the idea is very simple to what I showed earlier. You can fit the tiles into the scratchpad memory or even the register file if you compute on a GPU. But if you compute on a general purpose processor, you can actually do this in a L1 cache also. And the idea is you divide things into tiles. You do the multiplication of this tile and this tile first, and the result goes to this tile. And the idea is this is much smaller than your cache. That's good. And then you move on to the consecutive tiles to compute some of the points over here. That's the idea, basically. And you can take a look at the code. Basically, you're operating on not the huge matrices, but submatrices. Tile or block is submatrix in this particular case. And the idea is to fit those submatrices in the fast memories. Fast memory can be cache, scratchpad. In case of a GPU, it could be the register file because GPU register files are huge, right? In fact, if you can take advantage of that, that's great. Okay, and you can see the code over here. And again, if you're really interested in this, there's a lot more in this particular lecture as well as Juan's course. Let's take a look at another example. Here, we're going to do something different. Restructure the data layout, let's say. So I show you this code. It's a very simple code. You have node. These are linked lists. It could be any graph structure. Basically, you're traversing a linked list in this particular case. You're searching for a key in the linked list, right? You basically fetch a node. You check whether the key contains the input key. If it does, you access the other fields. Let's say you're searching for some student or somebody, right? And then you figure out what's their name, what's their school, and there may be other stuff over there. If the key doesn't match, maybe the student number or something, I don't know, some number, let's say, then you move on to the next node. Now imagine this is actually a huge linked list, 1 billion nodes and unique keys. Bad programming practice, don't do that, but it's a good example for showing what I'm going to show. You do pointer-based traversals over here, clearly. So I will, if you look at this code, I will say that it has very poor cache hit rate, assuming your data looks like this and it's laid out like this. Basically, a node looks like this, and then the next node is after this node, next node after this node, let's say. This has very poor cache locality. Well, I'll go through this, not wait for your answer over here. Let's take a look at, let's analyze it. So what's happening here? Basically, whenever we fetch a node, we look at the key. So that's accessed a lot. And then we access other fields of the node if the key matches. Probably that's not the common case, right? Because we're searching for one key and there are 1 billion entries in this. And then we go to the next node. So that's probably accessed a lot. So basically the key and next fields are frequently accessed, where the other fields are rarely accessed. Now, if you look at the layout of the code here, these are consecutive in memory. Rarely accessed stuff is consecutive with frequently accessed stuff in memory. So basically, whenever you access next and key, whenever you access next, whenever you access key, key hits probably, right? Because you brought stuff from next, assuming that there's enough time. But you're not accessing name and school, but that's occupying a lot of your cache space, right? These are big character arrays, as you can see. So basically, these other fields, name and school, occupy most of the cache line, even though they're rarely accessed. And the problem is you're mixing frequently accessed data and rarely accessed data in memory in a linear fashion. Spatially, they're closely located. So how do you fix this problem? Well, one way of fixing the problem is separate the rarely accessed fields of a data structure and pack them into a separate data structure. Basically, separate what you expect to be frequently accessed versus rarely accessed. And this is what we do over here, basically, as you can see. The blue ones are frequently accessed, red ones are rarely accessed. And the really big pieces of data that are here are not are in a separate data structure with a pointer over here. That's the idea. So this code will have better locality because this node is laid out nicely, and the next node comes after this will be in the same cache block. That's the assumption, basically, hopefully, if you don't have completely random accesses, right? But random access, if you have random access, caching doesn't work anyway. Forget about that. So the hope is that nodes are laid out consecutively now, and you get better cache locality in a single cache block. Okay, so the question becomes, who should do this, right? And again, an astute programmer can do this, clearly. Compiler can potentially do this. How does the compiler figure out what is frequently accessed, what is not frequently accessed? Becomes an issue potentially. Here, based on the semantic properties that I told you, programmer can easily do this. Hardware, can the hardware do this? That may be a bit tough, right? But people actually have proposed hardware to do this also. Not easy to build, but potentially the hardware can figure out what are the frequently accessed fields. And who can determine what is frequently accessed? Of course, when the hardware does it, they don't change the program usually, right? You could, with a binary translator, you could rewrite the program, rewrite the binary at least, for the next execution potentially, right? And that is done with binary translators today, actually. But you could do it also under the hood without changing the program at all. So the question is, who can determine what is frequently accessed? And that's a tough question. In this particular case, programmer can do a great job, actually. Hardware may not do it easily, let's say, as easily. But it can also do it, because hardware has a lot of information, actually. But capturing that information may not be efficient. Programmer may capture that information a lot more efficiently. Okay, so let me talk about some better replacement and insertion policies also, and then hopefully we're going to conclude. So as I mentioned, we're going to get back to this missed latency and cost. And missed latency or missed cost is affected by many things, actually. There are two major things, though. Where does the miss get serviced from? And how much does it affect the processor? How much does it stall the processor? What level of the cache in the hierarchy? Does it get serviced from L2, L3, L4, L5 memory, remote memory? Is there row hit in DRAM, row conflict? So now what we have seen earlier actually affects the latencies a lot. Queuing delays in the memory controller and interconnect. Is it local versus remote memory? Where is it? Is it on this node in the rack, in a remote server, in a memory blade? And who knows what else? How much does a miss stall the processor is a different question. This depends on your latency tolerance, right? Is the miss overlapped with other latencies, other misses? Is the data immediately needed by the processor? Is the incoming block going to affect a longer to refetch block? So basically, there's an issue here. It's an opportunity cost also. If you service a miss, and then it's going to evict something that's going to be much longer to refetch, you should be perhaps more careful. I'm going to look at one aspect of this, and that's the aspect of memory level parallelism. So today's processors can generate many memory operations concurrently, right? As a result, some operations may be serviced in parallel. Their latencies are overlapped. Some operations may be isolated. Now, if you just look at this picture, the timeline, the latencies of each miss is the same, ABC. Now, from the processor's perspective, if you remove A magically, the processor will not wait for A. So it gains performance immediately. If you remove B, it's not going to gain much performance, right? Because it's going to be bottlenecked by C anyways. So if you want to ensure that the processor is not going to wait for B, you should remove C also. Basically, if you want to improve performance by removing B, you should also remove C, because B's latency is mostly overlapped. So this basically immediately shows you that this isolated miss is much more expensive from the process perspective. Or if you remove it, you'll actually improve performance. Whereas parallel misses, their latencies are overlapped, and you need to remove all of them if you want to improve performance. And this is the notion of memory level parallelism. Memory level parallelism works by gathering together many misses like that and ensuring the processor doesn't stall for each one of them in an isolated manner. Okay, so basically some misses are isolated and some in parallel. The question is, how does this affect cache replacement? So it's very interesting, actually. So traditional cache replacement policies try to reduce miscount. An implicit assumption is this: reducing miscount reduces memory-related stall time. And this actually is not true, basically. Misses with varying cost and MLP. In this particular case, we're going to look at memory-level parallelism, but cost also is similar, breaks this assumption. So eliminating an isolated miss helps performance much more than eliminating a parallel miss. And eliminating a higher latency miss could help performance more than eliminating a lower latency miss. So when we actually looked into this, we cooked up this example. It actually happens in some real programs. Let's go through this relatively quickly. So you can see that there are some misses that are in parallel, P1 through P4. These are blocks. There are some misses that are serial, isolated, let's say. And this is what the program does. I cooked this up. The program basically accesses the blocks in this manner. You can see the numbers and the blocks. S1, S2, S3 are different blocks, and P1, P2, P3, P4 are different blocks. And it keeps doing this repeatedly. Now assume that we look at two different algorithms. One minimizes the miscount, Valdez optimal. Remember Valdez optimal we talked about. And the other one reduces isolated misses. Basically tries to get rid of these pink misses over here. It doesn't try to get rid of the green misses because pink misses are more costly. So if you have a fully associative toy cache containing only 4 blocks, let's take a look at what happens. So basically, I'm going to simulate it from steady state. You can actually verify it later on. We're going to assume all of these are hits in the steady state. Valdez optimal replacement, by just looking at this access pattern, this is the state of the cache at this point, again, steady state. It would replace, basically, here, it would replace P1, right? Because P1 is going to be a reference furthest into the future. At this point, the one that's going to be a reference furthest into the future is P1. So P1 will be replaced with S1. But S1 is a miss because it's not in the cache. Here, S2 is a miss. It's not in the cache. S1 will be replaced by S2 because S1 is going to be a reference furthest into the future at this point. And then S3 is a miss because it's not in the cache. And then S3 replaces S2 in the cache. This is the state of the cache at this point. And then you get 3 hits at P1 misses. Now P1 replaces S3. And then you're back to the steady state that we have shown, and it repeats basically. So basically, this is what happens. You get 2 stalls. One stall over here for these serial misses because they're overlapped mostly, and 3 stalls for these parallel misses. One stall over here for P1, and 3 stalls over here for S1, S2, S3. So you get 4 stalls and 4 misses. Okay, not bad. Now MLP aware, if you magically figure out these are serial misses by collecting some information, you basically keep these in the cache and always replace something else. That's the idea. So here, S1, S3, S2 are in the cache. P4 is here. So you hit S1, S2, S3, bring them into the cache. P4 stays here. Here you get 3 misses because only P4 hits. And here you get 3 misses also because we're keeping S1, S2, S3 in the cache because they're very precious for us, right? We figured out that they're very important. We're replacing only P's. Now we have 6 misses over here, as you can see, but there are 3 of them. They're overlapped in bunches of 3, and your stall count is 2. So you basically saved a lot of cycles by managing your cache in a much more intelligent manner, right? The key is identification of those misses that are much more important than others, right? They're not overlapped. Okay, of course, the question now becomes, how do you implement this? That's the subject of this paper and other course, clearly. And this paper also shows that this is not the only thing. There are some cases where LRU is extremely important. So if you have an LRU-friendly access pattern, don't do this, please. So LRU is so strong, basically, in some programs. That's why we developed also a hybrid cache replacement policy that says, do this unless your program is extremely LRU-friendly, let's say. Okay, so there's a lot more to talk about in caches, but we don't have time. So you can find a lot more information online. Victim cache, as I mentioned, is a really interesting idea. But there's a lot more, and you can find them online also. So this is, I think, where I will stop because we don't have time. I'm happy to take any questions, though. So we may release a short lecture on multi-core issues from last year. It's probably only 10 to 20 minutes. If you're interested, you can look at it. But all of these issues are covered in much more detail in advanced architecture lectures. Okay. No questions? Everybody wants to go to the weekend, so have a good weekend, and I'll see you next week for the last 2 classes. Take care. Oh. Hello.
Is something like a 7-way associative cache actually done in practice? Because I mean, I imagine you save some energy, but also you don't gain anything in terms of
Yeah.
latency, right?
So the reason why people may do it is because they're restricted in terms of area, right?
Oh yeah.
And as a result, they may say, okay, we're not going to have, let's say, 64-way, but we're going to have 58-way because of that, right? So I've seen, for example, 3-way caches because of that reason. They were restricted by area. Exactly. Yeah.
But I mean, the latency doesn't change, right?
No, because you still go through the mux basically. Yeah. It's very. I mean, even if it changes, it may be very, very little, right? So that's, yeah.
That's what I thought.
Sure. You're welcome. Yeah, you too. Bye bye. No. Okay.